on lesson 33, part 2. We're actually on the worksheet, question number 5. Worksheet question number 5. And so what it says, create the graph of y equal sine x in the interval of negative 5 pi is less than or equal to x, which is less than or equal to negative 3 pi. Now, notice that from negative 5 pi to negative 3 pi is 2 pi. And so that's a complete cycle of the sine wave. What we don't know is, did we start at the beginning of a cycle or in the middle of a cycle, or where at in the cycle? So as we think about this problem, there's two different ways that we might think about it. We might think about this, the normal sine wave, and maybe we even forgot some of that, would obviously go to 2 pi. That is the period for a sine wave. And so we want to create five markers really, if we start with 0. So if we took 2 pi and we divided it by 4, that would give us pi over 2. So we need to make increments of pi over 2. So we have 1 pi over 2, and then 2 pi over 2, which is pi, and then 3 pi over 2. And so this is the normal sine wave, right? And then we began to go to our unit circle, and we began to think, okay, what is the sine of 0? And the sine of 0 was 0, so my sine wave started there. And we said, okay, what's the sine of pi over 2? And the sine of pi over 2 was 1, and we had a dot right there. And we said, well, what's the sine of pi? And the sine of pi was 0, and so we were back to 0. And we said, well, what is the sine of 3 pi over 2? And it was negative 1 because it changes signs, and that put us down here at negative 1 for 3 pi over 2. And then when we get back to here, we're at 2 pi, which means we're back to 0 again, and we had a sine wave. Now, when we try to think about what that's going to look like, way over here at negative 3 pi, if we kind of think about it, we would have pi over 2, negative pi over 2, negative pi, right? Negative 3 pi over 2, negative 2 pi. And then we would have negative 5 pi over 2 and negative 5 pi over 2. I missed the mark. And then we would have negative 3 pi. And then we would have negative 7 pi over 2. And then we'd have negative 4 pi. And then we would have negative 9 pi over 2. And then we would have negative 5 pi. Now, we don't necessarily draw that whole big thing. What we do instead of drawing all of that is we usually just do this. We usually would just say, okay, I'm going to start like this, and I'm just going to do a little ditty thing to show that there's a piece of my grid missing. And then I'm just going to say, well, negative 3 pi. And then negative 3, if we talk about halves, negative 3 is 6 halves. And so down 1 would be negative 7 pi over 2. And down 1 would be negative 8 pi over 2, which is negative 4 pi. And down 1 would be negative 9 pi over 2. And down 1 would be negative 10 pi over 2, which is negative 5 pi. And so instead of writing the whole thing out, we do the little ditty thing to show that there's a piece missing and go from there. Well, how are we going to think about, I want to take this, and I want to pick it up, and I want to drop it in there, and I want to know exactly how it's supposed to drop in there. You see, you can kind of do that. We know that when we're on an odd pi, where are we at? 0. And when we're on a 2 pi, 4 pi, 6 pi, we're at 0 again. And so we can kind of think if we took pi and shifted it, maybe we could figure out where we end up. Now, for some people, that's kind of hard. I got to shift this thing to that deal. And if I could kind of think about keeping going, I might could think, well, I'm going to do this and this and this and oh, this, and so that's where I'm at. If you could kind of keep your sine wave going, you could kind of figure out that at negative 5 pi, we're actually kind of right here, see, going down and back up. But mentally, that's a little challenging. So what's always the easiest way to make a graph? Build a table. That's really easier, isn't it? Instead of trying to think, I want to take that thing way over there in the red, and I want to figure out where I actually started on that to shift it all the way to negative 5 pi. It'd be just a whole lot easier probably to just say, okay, I'm going to take my theta, and I'm going to take my sine theta, and I'm going to start at negative 5 pi, and then I'm going to have negative 9 pi over 2, and then I'm going to have negative 4 pi, and then I'm going to have negative 7 pi over 2, and then I'm going to have negative 3 pi, and I'm just going to figure it out and build a table and then graph it. So let's kind of see if we can do that. I'm trying to show you more than one way. Shifting that graph is kind of hard for people in their mind a little bit. Okay? So let's think about just from the unit circle. If we're at negative 5 pi, that's, whoops, I went the wrong way, didn't I? Okay, you know that every way around is 2, so there's negative 2. Everybody good with me? Negative 4, negative 5, I'm at 0. Okay? Now, all I'm doing is I'm doing a half move less. So I'm going to back up a half, negative 1. See what I'm doing? Back up, 0. Back up, 1. Back up, 0. So there's my values. And so at negative 5 pi, we're at 0. At negative 9 pi over 2, we're at negative 1. At negative 4 pi, we're at 0 again. At negative 7 pi over 2, we're at positive 1. At negative 3 pi, we're back to 0. And so I've graphed the sine wave in the interval of negative 5 pi over 2 to negative 5 pi to negative 3 pi. And so it would be like this. Or here, we would actually be down and up and down and up. And this would be positive 1, and that would be negative 1. Okay? So you might like a table better than trying to mentally think what part of that are we at when we shift it. That might not be so easy to think about. Any questions on number 5? We're still doing our unit circle stuff from memory, right? Notice on this test it says no notes or calculator. That way you have to know your unit circle rules. Okay? There's no reason to need a calculator or anything. If I let you use a calculator, you could graph it and hit trace, and you could find them all and not have to know your math. We want you to know your math. Okay? Any questions on number 5? Okay? So, on number 6, I'm not going to go through all that shifting the graph thing. We're just going to build a table. We have y is equal to cosine of x within the interval of negative 5 pi is less than or equal to x is less than or equal to negative 3 pi. And so we're going to think about our cosine wave, and we know that maximum and minimum on cosine is negative 1 to positive 1 again. And so we're going to go negative 3 pi. Don't forget that the period on cosine is still 2 pi, correct? The period is 2 pi. And if we divide that by 4, we're going to get little jumps of pi over 2. So we want our jumps to be pi over 2. So that's like negative 6 over 2. Negative 3 is negative 6 over 2. So then negative 7 pi over 2. Negative 8 pi over 2, which is negative 4 pi. Negative 9 pi over 2. Negative 10 pi over 2, which is negative 5 pi, right? We're reducing by pi over 2. So we just thought negative 3 is negative 6 pi over 2, and then we went to negative 7 pi over 2, and to negative 8 pi over 2, which is really negative 4, and negative 9 pi over 2, and then negative 10 pi over 2, which is really negative 5, right? So it's really not that hard to get the fractions. You just okay. Now let's build a table, and so we want to think about our angle theta, and we're talking about cosine of that angle theta, and we need to think about where we want to be. We want to be negative 5 pi, negative 9 pi over 2, negative 4 pi, negative 7 pi over 2, and negative 3 pi. And we're going to recreate this from the unit circle. And so we're talking about cosine. Let's just do our quadrantal angles for cosine. What is the cosine of 0? 1. Of 90, or pi over 2, 0. Of pi, negative 1. Of 3 pi over 2, 0. So that's memory work. 1, 0, negative 1, 0. And that's the numbers we're going to get, okay? That's the only numbers that's going to pop out in our table. We're just going around, okay? But negative is going around backwards, okay? And every 2 takes us all the way around. So on the negative 5, you're going to go around twice and then a half more, right? So let's just draw a picture. We're going to go counterclockwise. There's 2 pi, negative 2 pi. Around again, negative 4 pi. Halfway around, negative 5 pi, negative 1. Now, we got to unwind by pi over 2's. So we're going to unwind pi over 2. Next number is 0. Pi over 2. Next number is 1. Pi over 2. Next number is 0. Pi over 2. Next number is negative 1. Okay? That's the easiest way to do it in my mind. Get your quadrantal angles written down. Start spinning around counterclockwise. One round, negative 2 pi. Second round, negative 4 pi. Halfway around again, negative 5 pi. That puts me at pi, which is negative 1. Unwind, 0, 1, 0, negative 1. You can just keep going, okay? So, negative 5 pi is at negative 1. Negative 9 over 2 pi is at 0. Negative 4 pi is at positive 1. Negative 7 pi over 2 is at 0. And negative 3 pi is at negative 1. And so it's going to look like this. This is the answer. We just used that table to make sure we got the right points. And we did every bit of that out of our head. Notice we didn't punch a calculator. We just did all that from memory work. Okay? Any questions on 5 and 6? Okay, this part was given that we're going to graph the sine wave, the cosine wave within that interval. So the distance between here is 2 pi, which is the period, right, of a sine wave. Notice we're trying to create, we're trying to create 1, 2, 3, 4 gaps. See that? If we take the interval 2 pi and divide it by 4, 2/4 is 1/2. That means my little gaps are pi over 2, pi over 2, pi over 2, pi over 2. Now, the -5 pi is actually -10 pi over 2. So if I increase by pi over 2, I'm one bigger, which is -9 pi over 2, then -8 pi over 2, -7 pi over 2, -6 pi over 2, -5. And then some of those reduce and some of those don't. Okay? Any other questions? Okay? Now, the next thing that's going to pop up is this. You remember way back on page 95 of my Algebra 1 book, we had y equal x, and we called that the parent function of a line. And we said, okay, that's understood to be y equal 1x plus 0. And we said, if you were to add 2, what's going to happen? Shift up 2. It's a vertical shift. We said, well, what if you said, well, let's make this y equal 3x plus 2. Now what's going to happen? It's going to shift up and get steeper. And we said, well, so we got a vertical shift, and we got a, steeper, right? And then we came over to page 194 and 195 of my algebra book, and we said, okay, we're going to introduce to you y equal x squared. And we said that's the parent function of a quadratic. And we said if you took that and you added 2, what's going to happen? Same thing, shift up 2. And what if we put a 3 right there? The wings get steeper, so the parabola gets narrower. And then we said, well, let's introduce to you the graphing form of a quadratic. And we said that this causes a what? A vertical shift. And this is going to cause what to happen? Y is going to increase by some multiple. And we said that this little number right here is going to cause a horizontal shift in the opposite direction of what you see because of that minus. And then you may have learned that if there's a number right here, it's going to cause a division in the value of x. You're not dividing by x. It's going to cause a division. Okay? And so then we summed it up like this. When we looked at transformations of parent functions, we said, okay, if we had y is equal to a times, and I'm just going to call this bx minus h quantity square plus k. We said if you had a point xy, and let's just call that point f, that point f would map to what? If you put point xy under the transformation that included this stuff, then what would my new location of xy be? If xy was a parent function point, where would x end up? X would end up at, you do the inverse order of operations, you would undo subtraction and undo multiplication. So my new x would be my old x plus, you're going to undo subtraction by addition, my old x plus h divided by b. That's where x would end up. Whatever parent function x you had, you could find where it ends up by undoing what's inside the parenthesis in the reverse order of operations to x. Remember doing that? And then we said if you want to find out where y ends up, you take your y and then you're going to do in the order of operations. Well, that means that we're actually going to do the multiplication and the addition. So my new y is a times my old y plus k. So the parent function point xy would transform into the new point x plus h over b, comma, a y plus k. Now, I actually programmed the graphing calculator to do this, but I haven't ever showed you that program. I'm probably not going to, but it's kind of a neat little program that will transform parent function. You put it in and it'll just do the whole thing. It's kind of cool. Anyway, but that gives us an idea. Now, if we can do that to a parabola and a hyperbola and a square root and an absolute value, remember all that junk, then guess what? We can do it to also trigonometric functions. Now, so let's begin to talk about that. Let's say that we had y equal sine of an angle. Let's just put sine x. What if we added 6? What's going to happen to my sine wave? It started here, right? It's going to shift up 6, just like everything else did. What would happen if I put a 3 right here? My y's get bigger by a multiple of 3. Now look what happens. What was the maximum y? 1 and negative 1. What's it going to be now? Forget this transformation. Let's take that out. 3 and negative 3. It causes the amplitude to increase by that factor. You see? Because what happens to y is just going to get multiplied by that. So my maximum and minimum y just increased by a factor of 3. So your amplitude was affected by that number right there. Now, this causes a vertical shift, but that causes an amplitude change. If you put both of those in there, it would shift up 6, and then it would get, it'd be kind of like that, right? Except I missed, yeah. Okay? All right. So we go, oh, okay. What if we got really fun? Let's say we had y is equal to a times, a times the sine of, let's just say we had, I got to get my letters right. I forgot what letter they used. I shouldn't have forgot, but I did. I think it's a D. It's a K and a C. Give me just a second. I want to get all my right letters. Okay, they're using K. Okay, so let's say we had a sine K theta minus C plus H. Forgot my letters. I know what happens. I forgot what letters they use. That's crazy. Let's say we had a times sine K theta minus C plus H. It's different letters than they had on the quadratic. On the quadratic, we had A, B, H, and K. And now we got A, K, C, and H. All your letters are in a different place. Okay? It's kind of confusing. But anyway, so let's try to think about what would happen. What would happen graphically if you did this? Shift up. What would happen graphically if you increase that? Amplitude would get bigger. What would happen if you increase that? Horizontal shift. It would shift. If you made it bigger, the opposite of a negative, which would be a positive, to the right, so much. What would happen if you increase that? Now, the x's are going to get multiplied or divided. You see, if you see a minus and you make that bigger, you do the opposite, which is add. So it's going to be a shift to the right. If you see a multiplication, it actually causes a division on x. So your x's are going to get smaller. So you can have a smaller x with a bigger y. Are you kind of getting the picture maybe that my x's were doing this? But if my x's are getting smaller, I'm kind of crunching things up a little bit. Okay? All right. So now let's play with that on the graphing calculator for just a second and try to verify what we're talking about. So we're going to go to the graphing calculator, and then after that we're going to do some GeoGebra stuff, which is a really cool visual that we have here of this. I need to find my calculator. Bear with me. I guess I could pause, but you're trying to get yours up anyway. So all right, so we're going to clear it out. I'm going to hit second plus 7 1 2 enter, clear. And we're going to do these things one at a time just to try to verify what's going on. So I'm just going to go to y equal, and I'm going to hit sine, and then I'm going to put my variable button. So we're going to look at the sine wave from a graphing calculator. Now we need to make the window fit the data. So let's talk about that. So we're going to hit window. My x values, what are the normal x values for a sine wave? 0 to 2 pi. Remember, we're in trigonometry now. 0 to 2 pi. So I'm going to say 0 to 2, and then I'm going to hit pi, which is second up arrow. Second up arrow is pi. I typed in 2 pi. And I want to go in units of pi over 2. Second pi. Now this is going to really be important that you actually put in 0 to 2 pi and pi over 2 so we can actually see those 4 chunks. So everything lands exactly where we wanted it to land. Everybody see that? Now, the y only goes to 1 and negative 1, right? So let's just put negative 2 and then positive 2, negative 2, and positive 2, and units of 1 is good. They see that? And then we're going to hit graph, and there's a pretty little sine wave. Now, we made it work just like we did on paper, okay? Your numbers are going to look weird because you're talking about half a pi, half of 3.14, blah, 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 blah. It's 1.5, blah, 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 okay? All right, now let's go back to window, and let's actually go from negative 4 pi to 4 pi, because we may shift left and shift right and shift up and shift down. Yes, I missed. Yeah, thank you. Yes, got you. See ya. I still missed. Negative 4 pi. Got you. See you later. That's not everybody that's listening to this video. That 4 pi. Got it. Negative 4 pi to 4 pi in units of pi over 2. We'll get this right. There we go. Let's make our y minimum negative 10. It may look a little weird, and our y maximum positive 10. So we can just kind of deal with any shifting thing we got. Enter. Do what? X scale is 1. That's fine. Oh, my X scale. I made it pi over 2. Because that's the normal jumps we're making on a sine wave, right? All right, everybody good with that? So we're going to hit graph, and that just gives us a whole bunch of waves. Now, let's talk about what's going to happen, see if we can guess what's going to happen before it happens. So let's say we're going to go out here to the end of this and put a plus 2. What's going to happen to the sine wave? It will shift up 2. You see that? What would... So what would happen if we subtract 2? It's going to shift down 2. All right? Y'all stay with me here. Some of you got off track here. So let's say that we had 3 sine, not sure. Let's say we had 3 sine x. What did we say that's going to do? It's going to make all the y's 3 times bigger, which changed my maximum and minimum from 1 in -1 to 3 in -3. So it's going to change the amplitude from a 1 to a 3. Okay. What would happen if we took that out? Let's go back inside and let's put a -4. Well, let's put a -1 just so we can kind of try to see. What's that going to do? It's going to affect the x in the opposite of a -1, which is a +1. So it's going to shift the entire thing to the right one. Now this inside's affecting x in the opposite of what you see. It's going to be a horizontal shift to the right one. Understand that? Well, you may say, well, I can't see that. Well, let's go back and let's put our sine in there, sine x. So we can compare it. Now we can see that everything actually shifted to the right one. Okay? Now, let's go back and clear those out. And let's say, let's put sine of 4x. Now, what's going to happen is your x's are all going to get divided by 4. You understand that? The y's stay the same. All the x's get divided by 4. So every y has a smaller x. That may be hard to think about what's going to happen graphically. Let's go back before we do that and look at sine x again. I'm going to go ahead and put sine x in. I'm going to go up and turn the top one off. If you go on top of that, you know you can tap that in and hit enter, and it'll take the black off of it, and that turns it off. So I'm going to hit graph and just look at the normal sine wave. Okay, what's going to happen when I put 4 times theta? Let's go back and turn it back on. It crunched it up because my y stayed the same. What did that do? We're going to get 4 times as many doodadleys per period, right? Because it's going to do a full period in 4 times less x's than it used to take. You see? It's going to go through a cycle in 4 times less x than what it used to, which means when we get to 2 pi, there's 4 times more cycles than there was before. Because what's really happening to x is the x's are 4 times smaller than they were, so everything happens 4 times faster. You're getting to stuff 4 times faster because the x's are 4 times smaller. I know that sounds weird. So you're kind of getting the idea that that the parent function transformations happen with sine, cosine waves exactly like they did everything else. The confusing part then, as you noticed, I couldn't remember what all the letters were, are all the letters changed. What used to be H may be K, and what used to be K may be C, and what used to be C may be D. So we have a new set of letters to memorize for trigonometry. But mainly we want to memorize what happens in a certain position. You know, if we add something to the end, it doesn't matter what you call it, it's going to be a vertical shift. And if you do something inside the parenthesis, like add or subtract, it's going to be a horizontal shift, no matter what letter you call it. So if you understand that, you can figure it out, no matter what letters they throw at you in the formula, okay? I think I'm going to show you one other thing, and then we're going to stop here. I want to show you a GeoGebra applet, if I can get the right one. I don't want to do that one. I want to do linear quadratic. This is the parent function of a line, the parent function of a quadratic, and the parent function of an absolute value. The absolute value is in green. And what we learned is if we had something of the general form, like y equal x for a line, that's the red line, or for y equal absolute value x, that's the green, or y equal x squared, that's the blue. If we called this A and C for a quadratic, which is actually M and B for a line, but if I let that be A and C, then what we're going to see in this investigation is that if we increase the A, maybe I wrote those backwards. No, let's go back. If I increase the C, it's going to cause a vertical shift no matter whether I have a linear, quadratic, or absolute value. And if I increase the A for the line, the slope gets steeper, so the line gets steeper. For the absolute value, both wings got steeper. For the parabola, both wings got steeper, so the parabola and the absolute value got narrower. So if I make it even bigger, it gets even steeper, so narrower, steeper, and narrower, steeper, narrower, steeper, narrower. And so we learned all of that stuff. And you're going to see the same kind of thing happening to your sine wave. You're going to have sine waves getting really steep or really repeating itself faster, that kind of thing. All right, so let's find the GeoGebra applet for trigonometric stuff. Give me 1 second so we can see that. Okay. I want to try to take that back to a normal sign. Notice that if we were to see, it's got A, D, B, C. If I make A bigger, what's it going to change? Amplitude, right? It causes all my y's to get bigger or smaller by a multiple. I'm changing amplitude when I change the A. When I change the B, what's it going to cause? A horizontal shift. When I change the C, what's it going to cause? Vertical shift. When I change the D, what's going to happen? My x's are going to get smaller by multiples, so this curve is going to repeat itself faster. Okay? That's a pretty good visual aid. This is sine, cosine, and tangent. All right, we're going to stop there. That's actually lesson 34 and 35. I was just kind of giving us a head start visual of that. When we actually make that happen, we're going to make it happen with formulas and table building. But at least we have a picture in our mind now of how it connects to everything else you've ever learned. All right, appreciate your attention.